And as you will expect, in two-film theory, we're going to use mass transfer coefficients. In commercial absorption equipment, it's much more likely that you encounter turbulent flow rather than a laminar flow, so that's why we tend to use mass transfer coefficient rather than Fick's law or molecular diffusion. And well, we have seen this a lot, but just to remind you, remember that this is essentially molar flux of the species of interest, which in this specific case will be the gas acting as a solid, going from the gas phase to the liquid phase, its mass transfer coefficient, and the driving force. So the interesting part, as you can see, we have gas and liquids. For the liquid phase, we have either molar composition in the liquid phase or concentrations. And for the gas phase, we have either molar composition in the gas phase, we have partial pressures as well as concentrations. At any point, XAL and YAG will be the characteristic point in the compositions. We can write the mass transfer equations depending on what phase do you have. And remember, we have the gas phase, interphase, and liquid. If you're talking about gas phase, then you will need to use the coefficient of gas phase and the change in compositions with respect to the gas phase and the interphase. So technically this will be the bulk phase or the bulk composition. And then for the liquid, we need to use Kx, and as you can see here, you will have the one of the interface. Very important that if you were to go from left to right, and this is strategically, typically we tend to use gas in the left side and liquid to the right side, but does not necessarily has to be that, but this is just to have a coordinate of mass transport. Therefore we have the YA in the bulk phase, we have YA in the interface, XA in the interface, and XA in the bulk phase. So you can see here in the interface we have here to the right for the gas, and for the liquid we have it to the left. And finally the bulk phase composition. Here they go, molar flux of the component of interest, typically the gas. This will be measured in mole of A divided by area divided by time. Ky and Kx we already know that we'll adjust according to the changes, for instance, in driving force and the molar flux. So given that the molar composition does not actually has units, Ky will have the same units as N and Kx as well. The driving forces in this specific case were given in molar compositions. I'm going to start with molar compositions because typically that's what we will encounter in the equilibrium curves.